Okay, so I will going to talk about foliations. The aim is a complex foliation, holomorphic foliations. But before I start, I just want to recall you that the organizers had sent you a PDF file with my lectures. Okay, so it's huge, it's 80 pages. So no question that I will be able to cover all this material. And moreover, I'm going to use it when not giving all the proofs which I state. Not all statements which I will state on the blackboard. I will not have time to prove them. But detailed proofs are in this booklet which I had sent to you. Now, this is the first point. A second point is that supposing that this topic is new for you, it would be not wise to start with holomorphic foliations. One should explain few basic things from real foliations, from the part which was developed about 120 years ago. And there are three main results in foliation theory which one should know before one starts to go further. These are Poincar Bendixson Theorem, Haefliger Theorem, and Novikov Theorem. So I'm going to tell you these three theorems during my three lectures, and then I will give you two more results in holomorphic foliations. So the first lecture is the Poincar-Bendixson theorem. We consider a simply connected surface, real surface, with piecewise smooth boundary. So you know that simply connected surfaces are either sphere or a disk, homeomorphically. Okay. So now, since we are not working homeomorphically, so our surface will be like that. This will be denoted as S. S can be sphere as well. So it is not excluded the case when S is a two-dimensional sphere. Also, we don't exclude the case when S is a disk, the unit disk. In the first case, there is no boundary at all. In the second case, boundary is smooth, the unit circle. But for our applications, we will need a little bit more general settings. We consider a vector field, V, of class C1 on this surface. We suppose about this vector field the following. On every boundary point, which is not a corner, this vector field is pointing inside of the surface, or is tangent. It may be tangent. At corner points, so let this be corner points, S1, S2, and so on. At corner points, vector field vanishes. V of Si is 0. And it can vanish inside at some finite number of points, E1, E2, and so on. So our vector field vanishes also with these points. The points where vector field is vanishing we called an equilibrium points. The set of equilibrium points we denote by E. More precisely, the set of equilibrium points which are inside in the interior of our surface. Okay. Well, boundary points, well, we don't speak about that. Well, this is our setting. And now, okay, one more point I forgot to tell you before. I know that there is an exercise section after the dinner, yes? So, in every lecture, there are some exercises. So we can discuss them, yes? I will not state these exercises on the blackboard. Okay, so now having a vector field, we can consider the differential equation as usual, x point equal to v of x, and x at 0 is equal to the some initial point x0. So this is a ordinary differential equation. Okay, it's not good. Okay, thank you. This is an ordinary differential equation, and we know from the university course that it admits solutions continuously depending on the initial data and so on and so on. So I will use this stuff and I shall say what I need. So this system defines the flow. Now I'm going to tell you what is the flow. Flow is a mapping from R plus times S to S. For every x, so this is like that. Phi t of x is a solution of our system with initial data. So solution, well, let it be star. Solution of the system star with phi 0 at x equal to x. Okay, in other words, well, you have a vector field which I'm not able to design, and solution is a trajectory. So it starts at point x, yeah, which is phi 0 at x, and then it moves somehow. It moves at point phi t of x. The derivative of phi t is equal to the vector field which we have at this point. Okay? This condition that we have, that vector field points inside to the surface, ensure us that all solutions are defined for all positive times, but not for negative, because if you have this solution here, it can go out in the negative time. Okay. If the tangent field is if the vector field is tangent at every boundary point, then solutions are defined also for all negative times. Okay. But in this case, solutions are defined for the positive times. And one says that this is a flow. Giving a flow is the same as giving this equation. It's equivalent things. One more point. So this is solution. And one point that if S is an equilibrium point, or E, if point X belongs to the set of equilibrium points, then solution is a constant. So then phi t of X is equal to X for all t. Okay. The set of points gamma plus X, which is the set of all phi tx, t in R plus, is called the half trajectory. Is called the half trajectory. So it is as here, as half trajectory which starts at x. Okay. And now the first notion we shall need is the notion of the limit set, omega of x. It's a set of all limits, is the set of all y's in S, such that phi tn of x tends to y for some tn going to plus infinity. So all possible limits of our trajectory, so trajectory goes like that, and all points which are limit points of the trajectory we call the limit set or the omega limit set. One can prove that this is the same as the intersection over all positive t's of phi s of x s bigger or equal than t, so and closure. So you take a trajectory which starts from point t, a piece, then you take the closure of this, and then you take intersection of all. And this will be the same. It's easy to prove. And from this description, it follows proposition one. It follows that the limit set is the same, omega x is the same as the limit set of any phi t of x. Yeah, okay. Well, this is obvious. You have a trajectory which starts at x, and you look on all limits of this trajectory. But this is the same if you start at phi t of x. It is the same trajectory. Okay. This is the first statement. Second statement is that omega x is invariant. Is invariant, I shall say like that. So what does that mean? Okay, let me state the last statement, and then omega x is connected. Well, this last thing follows from this description. Intersection of connected sets is, or decreasing sequence of connecting sets is connected. And invariant means that if y belongs to omega x, then the health trajectory, the all trajectory gamma plus of y belongs to omega x. So y is z. So you have y, and it can be approximated by our trajectory. What that means? So you have x, and you have trajectory which goes closer and closer to y. Okay. But then if you take the trajectory which passes through y, then this trajectory is approximated by the trajectory which starts at x. From the theorem of the continuous dependence of the solutions of differential equation, it follows that this trajectory approximates trajectory which goes through y, and therefore the whole trajectory which goes through y is in the limit set. So the limit set is invariant. Okay, now one more point is the following. Consider a smooth map from the open interval, I shall call it I, to S minus equilibrium sets. So, okay, I have like something like that. There are some equilibrium point away. I don't consider it for the moment. And let this map be such that derivative over dt at every point is transverse to the vector field at this point. So like that. Image of I shall denote by t. And this t is called transversalis. Transversalis. A transversalis to our vector field. Well, it has some direction. The same as direction of the interval. Okay. And now, what we know from ordinary differential equations, we know that we can find a neighborhood U. So I forgot to tell. Let x be some point. We fix some point which is regular, which is not equilibrium point. And we take a local transversalis to this point. If we take it sufficiently small, then we can find a neighborhood which can be mapped by a diffeomorphism psi. So if our vector field was of class C1, it will be of class C1. And the image, the flow, the integral curves or trajectories will be the straight lines parallel to the axis x, and the transversalis will be mapped. Okay, x will go to 0. Transversalis will go to the vertical interval, and trajectories to the horizontal intervals. Okay, this U is called a flow box. Okay. And these pieces, well, as the pieces of trajectories like that, either here or here, are called the plaques. It's a French word. Or plaques, I don't even know how to pronounce it in English. Yeah.
Maybe a stupid question, just why it's an assumption that if x in x, phi t of x is equal to x, you know, here
What is?
in the left, here, yeah, like here, if x is in sigma,
X is.
x is equal to x, here. Yeah,
No.
I don't understand that.
No, okay, so it's not an assumption, but if your vector field is 0, yes, vector field is 0 at this point. It's, if x is an equilibrium, exceptional point, where v of x is 0 at this point, so the function constant x will be a solution. And it is the only solution by the uniqueness.
Because v and v is
V is of class C1, okay, it can be Lipschitz. Well, C1 is sufficient. Well, I hope. Yes?
The transversalis is transverse
to the trajectories, to the flow. Yeah. Transversalis, yeah, I forgot this definition. It's just a line which is transversal to the trajectories of to the solutions of our differential equation.
and it goes through x.
And it goes through x. I take point x and okay. You take some point x, which is not equilibrium, and then you can draw a transversalis. You have a lot of possibilities to draw this. Okay. Okay. And now the theorem comes of Poincar Bendixson. In the conditions as above, means that surface is simply connected with piecewise smooth boundary, and vector field is as here of class C1. Okay? In the conditions as above, suppose additionally, but then we shall remove this assumption. Suppose that the limit set of the trajectory which passes through point x does not intersect the set of equilibrium points. So suppose that a trajectory which you take stays away from equilibrium points. It never approaches them. This is some, for the moment, additional assumption, but it's a classical way to state the theorem. Then omega x is a periodic trajectory. So it's something like that. It's a closed curve which is a trajectory of our flow. And so you should think as follows. You have some point x, and you have a trajectory which goes through x, gamma plus of x. And then this guy goes closer and closer to something, which is omega x. And it turns out that it can be nothing else but a trajectory. a smooth trajectory. Okay, proof. So there will be 4 steps in the proof. Only in the last step I will use this assumption that omega x stays away from the set of equilibrium points. Okay. Okay, let us remark that if gamma plus of x is itself a periodic trajectory, is itself a periodic trajectory, then there is nothing to prove. Okay, then we are finished. So for the sequel, we suppose that gamma plus of x is not periodic. So it goes like that. It never ends. So lemma 1. Fix some y which belongs to the limit set but is not an equilibrium point. Well, as I said, this condition will be used only in the last step. So now I admit that the limit set can have equilibrium points, but I take the point which is not an equilibrium. Let T be a transversalis through y. Okay? You have if I have a point y which is not equilibrium, I always can draw some small transversalis. So no problems. So y. And let T0 be such that phi T0 of x belongs to transversalis. Well, such T0 always exists. Why? Because I permit myself to erase this x and to write y here. So I took some point y, which is not an equilibrium. And I know that my trajectory approaches this point. So it comes like that, repeatedly goes through this flow box. So it necessarily intersects my trajectory. So I take a point, let's say, okay, let me give another y0, and I have trajectory which approaches this y0. I take some transversalis through y0 t, and I take some point of intersection. So I take some t0 such that this is phi t0 of x. And my trajectory starts at x. Intersects E, then it stays. If you arrive to the, then it stays at this point. Then we are finished. Okay? But it can approach an equilibrium point. And we shall consider this case after that. But now we suppose that limit set does not intersect the equilibrium point, that means that gamma plus stays away on some distance. This means that.
It did not approach a regular point. It's not a limit.
No. In this lemma, I suppose that we approach a regular point. I suppose that we approach a regular point, and now I want to say something about how it works. And I take the first, well, I don't say it's the first point of intersection. I take some point of intersection of my trajectory. This is trajectory gamma plus of x. And this trajectory has y in its limit set. I take some t0 that this point is on the surface. Then claim is there exists t1 which is strictly bigger than t0 such that phi of t1 of x is again in the transversalis, like here. This will be phi of t1 of x. And for all t in the interval between t0 and t1, phi t of x does not belong to the transversalis. So, in other words, if you cut transversalis at some point with parameter at time t0, then you will cut it next time and never in between. And this t1 is called next to t0. Well, what is the proof? The proof is obvious. You arrived at this point. So you take the trajectory, which goes like that, and you wait until it arrives again to the point of intersection. It must arrive because this trajectory approaches y. So there will be another point which arrives to this trajectory. But between any 2 points, look, we have a flow box here, like there. We have I don't want to write this. We have a flow box, so you cannot pass through this flow box in 0 time. There will be always some epsilon, then you need epsilon to go out from the flow box. So the next t1 to t0 cannot be arbitrarily close to t0. Well, more or less that's it. Okay. Now, second step is more important. Lemma 2. The set t0, t1, t2, and S1, which is phi of S0, phi 0 of x, S1, which is phi t1 of x, are if this set is monotone, which you can always take. You can always take this set to be monotone because phi t of x approaches y. So then, but then the set is monotone as well. Now, what does it mean, monotone? The set of time, the real line is have the order. So you can say what does it mean that t0 less than t1 less than t2 and so on. But the interval transversalis has also order. And the claim is that monotone, well, you have two possibilities. Either this S0 is less than S1, less than S2, and so on. Either S0 is bigger than S1, bigger than S2, and so on. So anyway, that means that you have a picture like that. And you continue, and you go closer and closer. You cannot go inside and cut somewhere here because of the Jordan theorem. So if you take a set like I draw with a red pencil, if you take this is domain D. So it is the case when t0 less than t1 and S0 is less than S1. This is S0, this is S1. But then you see that you cannot enter here, and then forcibly S2 will be bigger than S1, and so on. And this is the proof. So trajectory cuts transversalis by a monotone sequence, just one after, and which approaches to the limit point to y. Okay? And so
Can I have a question?
mm-hmm.
Could y be on the boundary?
Yes,
Yes, it's good.
yes. It can be a boundary point.
And everything will work. The transversals will exist.
Yes, everything will work.
Okay, thanks.
Yes, thank you for the question. Well, now, lemma 3. If y is a limit point which is not equilibrium, then the complete trajectory means positive trajectory and negative trajectory exists and belongs to the limit set. So the limit set contains with each its regular point the whole trajectory which coming through this point. Well, why is that? Let y be the limit. Y be the limit. Then what you have? Then you have a trajectory which is approaching like that. So you take trajectory which goes through y. And remember that locally you have a flow box. Everything is parallel here. So the whole trajectory is approached by your trajectory, which is was x. Your trajectory approaches a piece of trajectory through y. But again, according to the continuous dependence of the solutions of the ordinary differential equations, if you go close to y, the whole piece will go close to this trajectory. So you will approach the whole trajectory. Backwards, the same. If you go in this direction, still this guy is approaching you. So the whole trajectory is in the limit set. Well, and the final step. So the final step, so is a proof. So this is step 4. And now we are going to use the fact that all points in the limit set are regular. Okay? So let y be in the limit set. It's according to our assumption is necessary integral point. Then the trajectory through y, which we proved is contained in the limit set, is in fact equal to the limit set. Okay, proof. So we know that gamma of y is okay. Well, suppose we have some another point. Suppose y1 belongs to omega x minus gamma of y. Okay, suppose we have some another point. So this set is not empty. Then this set is open. Open, this set is open in omega x. Yes, because if I have, so why it is open? So let we take any point, y1, and I know that it's not in gamma y. And then I say that this set cannot be approached by gamma y. You cannot have that gamma y approaches y. Why it cannot happen? Because you take transversalis through y, and if this would be the case, you would have that your gamma y intersects this transversalis in different points. So let me make the picture here. So the trajectory gamma of y intersects your transversalis, well, in many distinct points, in fact. But what we know that trajectory intersects a transversalis by a monotone sequence. Okay? So gamma plus of x, this trajectory which has as its limit this omega x, in particular the whole this should intersect somewhere here and somewhere here many times. So this set will be not monotone. So this set is open, and So it cannot be closed. So omega x minus gamma of y is not closed. Because omega is connected. Okay, and now since it is not closed, it means that there is some point y1 in omega x minus gamma of y, which can be approximated by points in gamma 1, such that some points xn from this trajectory approach y. And this is again impossible by the same reason, because you can take transversalis through gamma 1, and then you have that this gamma intersects many times this transversalis, and this is again not possible. Okay. So the crucial, well, it's finished. So the crucial point in the proof of this theorem is a monotonicity lemma. This implies everything. If your surface is not simply connected, then you don't have monotonicity lemma. In my lecture notes, there is a simple example on the torus, and there you can have a trajectories which are dense in the torus, for example. Okay. And now I must say one more point. I must say more 2 points. So first point is you don't need this assumption. And let me state the theorem. Well, which is again theorem of Poincar Bendixson. In the conditions as above, so again, S simply connected, vector field is of class C1, and with finitely many equilibrium points. Let omega x be a limit set of gamma plus of x. Then we have 2 possibilities. First, either omega x is a singleton, is one point y, and then y belongs to the y is an equilibrium point, and gamma plus tends to y. Well, you have picture like this. This is your y, and this is spiral which goes to y. This is your gamma plus of x. And second possibility, omega x is an orbit or a polycycle. Or a polycycle. So what does that mean? That means something like that. A polycycle, so orbit is a periodic trajectory, and polycycle is a closed curve which consists from finite number of equilibrium points and trajectories between them. So let's say gamma 1. Well, it can be like, so okay, so it's gamma 2, and so on. And these trajectories are such that gamma 1 of, well, so it tends to one vertex when t goes to infinity and tends to another vertex when t goes to the minus infinity. These are trajectories of our vector field. Okay, it can be also like that. Well, for example, you can have the following picture. Okay. And then this is your x, and this is your gamma plus of x. And it accumulates to this triangle. You can have something like that. You can have only one vertex, for example, like that. This is equilibrium point, and this is a trajectory which starts, well, in some sense, which at minus infinity is this point, and at plus infinity is this point, and so on. You can have many pictures like that. The proof is not much, is not more difficult than that I gave to you. And second point, which I want to stay, is a following thing. Instead of vector fields, you can consider line fields. Yes? Yes. What? Yes? No. So this is your trajectory. It starts at point x and it goes like that. And in the limit, it is a triangle. No, it consists from three trajectories. It consists from three trajectories. What? Okay. And now, instead of vector fields, you can consider line fields. So at each point, you have a line. And you can do the same things. Okay? But now there is one difference. So if you want to reduce this line field, you may say, okay, you have line field, you write a vector, and you will have a vector field. No, it's not always possible. This is what I want to say. For example, you have this example. Yes, of course, if the line field is smooth, never zero, then you can always write a vector field. But it's not always the case. For example, this will be the trajectories of the line field. Okay? So your line field is such that these are trajectories. And there is one singular point, 0. Then you cannot find a vector field you cannot find a continuous vector field which is tangent to all these lines. Well, for example, if your vector field is like that, then this should be like that, but then this should be like that. So it is impossible. Okay? And one more example. Okay. This is again a line field with singularity which you cannot orient. You cannot find a vector field which is tangent to these lines. And the statement, which is given in my lecture notes, says, and which I shall need in my course, states that a locally lemma, a locally orientable line field is globally orientable. So, if you can find these vector fields locally near each point, then you can find a global vector field which will go along your lines. The short proof is given in my lecture notes. And I will need this statement because then I can apply Poincaré-Bendixson theorem, yes? For the line fields, Poincaré-Bendixson theorem is not valid. And there is an example in my lecture notes. Thank you.